We are continuing on with our discussion. In this discussion, it's going to be relatively, I wouldn't say short, but given that most of the things that we're going to talk about in this particular section here we've already kind of discussed, we're just going to look at some of the little caveats that we can use, or some of the tools that we can use to kind of affect how the database is updated, or the graph, if you will, is updated in Spanning Tree. We're doing this evening the OSPF NSSA Translator Election and Forwarding Address section. And that's what our focus is going to be on. We're still dealing with the not so stubby areas, and that's based on the last couple of sections that we've covered. But now we're going to talk about how the Type 7's to Type 5 translation election works. In other words, which device is going to do the translation, which ABR, how the forwarding address works, why I would want to maybe influence whether or not the forwarding address is suppressed on the ABR in the event that we're actually doing the translation from our Type 7s to Type 5. And based on changing that, how can we change the forwarding address to provide for traffic engineering? All right. If we're looking at reachability to the forwarding address and we lose that reachability to the forwarding address, how could this cause problems in the OSPF network in solving the tree and solving the graph to provide for reachability to those external destinations? So let's take a quick look again at our topology. I've kind of reverted back to the basic OSPF topology that we had originally without the redistribution on router 5 and router 3 for an external EIGRP domain. And router 3 is going to be our ASBR in this particular case. That's going to be sending in the 33333333 subnet or prefix from EIGRP. So let's start by taking a look at the graph. Let's see if router 4 even has reachability to that particular destination. Show IP OSPF database external 333333. We'll look at the details in this a little bit later on. We can see that the forwarding address is in fact established in this case, and we're going to the ABR of 5.5.5.5 to reach this destination. But we'll talk about the details of that and why that would be something that we would necessarily want to deal with or want to take a look at and maybe influence, because just because router 5 in this particular case is the one that's advertising or translating the Type 7 to Type 5 doesn't necessarily mean that that's the path that we are taking. In fact, if we look at the overall topology, it probably wouldn't make a whole lot of sense to go to router 5 to reach that destination because of the way we resolve the path along the way. Router 5 has a much higher cost link to get to the 33 network. Router 1 would probably be the preferred path. So let's see if we're actually hitting that 16.13 subnet in this reachability. So if I do a trace route to 3333, we can see that we're hitting that 16.13 subnet. So just initially, without even really discussing anything or without even really going through anything, we're seeing that ABR 5 is the one that's translating the prefix, but we're not using router 5 to reach that particular destination. All right, so that's just the only route that we have coming in from EIGRP. We're simply redistributing that route into the OSPF network, and both ABRs have visibility to that particular destination. Let's go ahead and check that out. We should have we should be able to resolve that destination within router 1 through our router, our LSAs, Type 7 LSAs. So if I do a show IP OSPF database, NSSA external on this device, we can see that 33 is coming in as a Type 7. And we can do the translation. The translation is certainly available. The routing bit is set on this particular advertisement, so that does mean that router 1 has the capability of reaching that destination using a Type 7 LSA. We'll go ahead and check router 5 as well. We should see a similar output. Show IP OSPF database NSSA external, and the routing bit is set here, also type 7. 33 is the external network, and we're doing a type 7 to 5. The P bit is set as well on router 5. So both router 5 and router 3 have the capability of doing this translation, okay? So this is a very interesting concept because we can control all of these attributes. We may decide that we don't want router 5 to be the one that's advertising the route. We want router 3 to be the one that's advertising the route. And then perhaps we want router 5 to be the path that we choose to reach that destination. So we're going to have to modify the forwarding address attribute to be able to get router 4, who's part of area 0, to decide to reach that destination through router 5 rather than router 3. When routes are generated, they're generated in the NSSA as an NSSA external route, which has an area local scope. That means that these routes are going to get flooded to all the routers in the area, but they don't get flooded beyond that area. The routes actually terminate within the area. And then we have to do some sort of translation that allows us to further extend those routes out of that area into the backbone area. So when we go to move the route from the NSSA into area 0, only one of those border routers of that NSSA is going to do the actual translation. Translation does not mean routing. That's a very important concept. Translation does not mean routing. On the back end, they're going to do some sort of election process to say who's going to do that particular translation. In the end, it really doesn't matter because there's a complete disconnect from who does the translation of the type 7 to type 5 LSA versus where the traffic is actually going to be forwarded. All right, we've already seen based on the current state of the network that router 5 is doing the translation. The P bit is set when the type 7 reaches router 5. So router 5 is doing the translation, but we're not using router 5 as our, to resolve the graph to reach that destination from our router in the backbone. All right, we're going to see how changing this election process is going to affect the forwarding and how the forwarding address also affects the forwarding in this particular case. We don't really have to clean up any of our config. I went ahead and did that as part of the preparation for this class. So I just wanted to make sure that it was you know, as clean and basic as possible, just to understand this general concept. It's highly likely, maybe, I didn't have anything like this on my exam, but it is possible that they might request that you manipulate the translator of these type 7 LSAs within a domain, within an NSSA domain, and that you somehow manipulate the forwarding address of these routes so that you can choose an appropriate path or choose not an appropriate path, but maybe a traffic engineered path to reach that particular destination. So we don't really have to spend any time kind of analyzing the topology here. All this is a regular NSSA. We've got essentially 3 routers that are participating in that domain, router 1, router 5, and router 3 in that area. And they're all just configured as standard NSSA routers. If we go to router 3, we're going to see on router 3 also that we don't have a default route. Let me see. Yeah, we don't have a default route in this particular case. So we're not sending a default route. We're not receiving a default route. So we're not doing any kind of default information originate or using some sort of aggregate address default route advertisement like we did in the last class. All right. So if we want to verify the information about the type 7s, show IP, OSPF, database, self-originate, we can see that router 3 is originating the type 7 LSA. And then I can see what that looks like from router, well, I have to do NSSA external, 33, 33, 33, 33. what that looks like from router 3's perspective. All right, the routing bit here is not set because we're not using OSPF to reach this destination on this router because it's a directly connected route. All right, so in the routing information base, we're using a directly connected route to reach this destination. Whenever you're looking at any LSA in the database, doesn't matter what it is, it's going to involve identifying whether or not the routing bit is set for that particular destination. All right? And in this case, it's not. So that means that we must not be using OSPF to reach that particular destination. We must be using another method to reach that particular destination. Okay? Now, as far as the metric goes, we talked about this in the previous class. One of the things that I'm looking for, if I do a show IP route to 33, 33, 33, 33, I'm looking for this forward metric, which is going to help me identify. It's coming in as an NSSA type 2, which is a standard for routes that are coming in as type 7 within an external domain. I'm looking for that forwarding metric to allow me to identify how I'm resolving the graph within the area, my intra-area resolution. So router 4 is using a type 4 / type 5 LSA to reach the ABR, and then the ABR is utilizing its type 1, type 7, type 1 LSA negotiation to reach that particular destination within the area. So we can see why router 5's path would not be chosen over router 3's path. It simply has a higher forward metric. Even though the seed metric for the route, if I come into router 4 and I do a show IP route, the seed metric for the route is very simple. It's a 20. It's a cost of 20. But we're not utilizing that metric to reach that particular prefix. Again, it's always about resolving the graph, routing to the nodes, not routing to the networks. If I do a show IP route, remember router 4 is the one that's in the backbone to 33, 33, 33, 33. We can see that the forward metric is listed as 21, even though the seed metric has a cost of 20. All right? And that has to do with reachability to the ABRs. And so we're not seeing, even in this particular case, how we're reaching that particular destination. All right, we're going to play around with this a little bit and identify perhaps if we can do ECMP, equal cost multipath routing, and see how that's going to affect our decision. All right. If we looked at the individual details on the LSA, which is what we did, we see that we're looking for that type 7 to type 5 translation is allowed. Again, going back to router 5, we can see that right here. Type 7 to type 5 translation is allowed. You recall from our previous discussion that indicates that that is the P bit. If it's not set, if that P bit is not set, then we're simply not going to advertise that route into area 0, at least not from that router's perspective. The P bit could be set in one direction, but it may not be set in the other direction. We did see from our previous discussion a couple of lessons ago that we have a couple of options to manipulate this. We could do the NSSA only option, which wasn't available in this particular iOS, or we could summarize, create some sort of false aggregate with the NSSA only to forcibly remove that P bit if we wanted to. The other reason that we could potentially remove that P bit, and we actually saw that as part of our example, which I don't have anymore here, but remember we had a link here. Let me grab my snipping tool. We had a link that was, or an EIGRP network that we had created off of router 5, and we had some sort of EIGRP router here, and we were doing redistribution on router 5, so router 5 was an ASBR, and router 3 was an ASBR in this case. And we were redistributing those 172 subnets that existed down here. So the only other reason that that P bit would be suppressed is if the ABR is also an ASBR. And I believe you guys remember we saw that as part of our output the last time. If an ABR is also acting as an ASBR, it's going to remove the P bit because it doesn't really want someone else doing a translation of a route that it's already advertising into area 0. So this router is already sending the route into area 0 as a type 5 because it's participating in the backbone. It's going to send it in as a type 7. We can suppress that behavior. Actually, we could suppress either behavior, right? We could suppress it going into the backbone, or we could suppress it going into the NSSA area with a couple of different options on a redistribution. But I don't want that route to come back over to here and then have router 1 kind of send that route in as a type 5 as well for the same prefix that I'm already originating going into area 0. We're always going to prefer our intra-area external LSAs over our inter-area external LSAs. And if I'm sending it over here and then sending it through router 1 into the backbone, that's going to be considered an inter-area external LSA. Make sense? All right. So we took a look at how router 4, in this particular case, sees the route to the external domain. We already identified, let's go back to here real quick. We already identified by looking at the external routes on router 4. Get rid of all these lines here. The external routes on router 4 that even though router 5 is originating that, or at least advertising that external route, this 33 subnet, we're actually going to take the path through router 1 down to router 3 to reach that particular destination. All right? The external type 2, because remember it's already being translated to a type 5, that's going to go through router X. We did a trace route. Why did it choose router 1 as the entry point into the NSSA as opposed to the other router? Assuming everything was equal and we haven't modified anything, which in this particular case is true, we haven't done anything with any of the information that's coming from the routers. We're not manipulating how the route's being advertised. We're going to choose it based on how we resolve the tree, right? I mean, that's ultimately what our goal is, right? When we're looking at external calculations that come from a router, by default, it's going to work differently than any kind of router that's generating a type 5 external route. So we know that router 3 is generating these type 7s. When we look at how we choose a path to a type 7, that's going to be completely different than how we look at a type 5 external route. And the reason is that a normal type 5 in the forwarding address is always going to be a quad 0. So let me show you what I mean by that. We've got redistribution that's occurring on router 2 as well, but router 2 is in a normal area. If we don't have it, we'll go ahead and configure it. Let's go ahead and check router 2 real quick. If I do a show IP OSPF database external, yep, I have, well, there's my type 3s, but I should see in my type 4s, but I'm not doing any, let me do one more thing. Show IP OSPF database self-originate. Yeah, I'm only generating type 2s and type 1s from this router. All right. All right. So that being said, let me do a quick show IP interface brief. And show IP OSPF interface brief. Show IP OSPF interface brief. So loopback 0 and Ethernet 1.0 participating in OSPF. So what I'm going to do is I'm going to create a loopback interface loopback 100, IP address 22.22.22.22/255.255.255.255, and I'm going to go into router OSPF 1. Let me do a show IP protocols. Can't recall which process ID we're using. 1. Okay, so router OSPF 1. And we're going to do a redistribute connected subnets. All right, so now I should be generating a type 5 in this domain, show IP, OSPF database self-originate. Yep, so now I'm generating a type 5. If I do a show IP, OSPF database external 22, 22, 22, 22, we always reference the link ID when we're trying to reference an external LSA. We don't use the router ID or the advertising router. We always reference the link ID. We can see here that the forwarding address is quad 0. And in fact, that stays that way all the way until we reach router 4. So if I go to router 4 and I do a show IP OSPF database external, we can see now, actually let's look at just the database in general. We can see that we're now getting 3 type 5s, one from router 3, one from router 2, one from router 5, and one that's self-originated, which is the internet route. All right. So what does that mean? Well, it doesn't really mean much, right? Router 4 is still trying to reach those external destinations. But if I do a show IP OSPF database external, and I include for 33, 33, 33, 33, pipe include forward, is maybe a capital F. There we go. And I do the same thing for 22, 22, 22, 22. You can see that one has that forwarding address set, the other one does not have the forwarding address set. This is pretty significant because it changes, and that's what I meant by what I said previously. It changes how router 4 decides to route to that particular destination. A normal type 5 LSA, which started as a type 5 originally, that forwarding address is always going to be a quad 0. All right? That means that we should route towards the ASBR that actually did the origination, and we're using our type 4 LSA, show IP OSPF database, those summary net link state LSAs to reach that particular destination, or summary ASB, sorry, excuse me, summary ASB link states. Notice we don't have a summary ASB link state for router 3. We only have a summary ASB link state for router 2, which is the one that's generating the standard type 5 LSA. So the way we recurse to those destinations is completely different based on that forwarding address. All right? When we're doing a type 7 to type 5 translation, it's a lot more complex because we're not going to try to advertise the route both ways out of both ABRs. We do want to advertise reachability both ways. So both router 1 and router 5 are going to say, hey, I know how to get to this destination, but we're not going to advertise the route both ways. We know we can go either way, but we have to choose the route based on the forwarding address. All right? And the forwarding address in this case, let's go back to 33, is 192.168.3.1. So if I do a show IP CEF 192.168.3.1, I can see that I'm going to 14.1 to reach that particular destination, which, by the way, is router 1, right? By the way, this is also the IP address of the router, not the router ID of router 3. All right, let's do a little experiment here. If I go into router 3 and I do a show IP protocols, I can see that the router ID has been established as 3.3.3.3. Now I can come in here and I can go into router OSPF 1 and say that the router ID is 33.33.33.33, right? And I'll do a clear IP OSPF process. We'll have to reform our adjacencies and kind of resolve the tree again. But if I look at the forwarding address, actually let me do the whole thing because I want you to show you the advertising router in this case. Show IP OSPF database external. We can see, it might take a little bit, yeah, there we go. right? Well, that's the external network. We're actually technically not going to see it in this case. We would have to go to router 1 and look at the NSSA external. Show IP OSPF database NSSA external. We can see that the advertising router is now 33.33.33.33, but again, the forwarding address is 3.1. All right, we've already cleared out the other false information because router 3 doesn't exist anymore, right? We changed the router ID. I mean, it's a simple concept, right? Router ID is not the forwarding address. The forwarding address is typically going to be the highest loopback on the router itself. Actually, we ran into that the last time, right? We saw that it maybe perhaps wasn't the highest loopback, but it was definitely a loopback because we went through the process of adding a loopback, I recall, in the last lesson to see if the forwarding address would have been modified. And I forgot to go out and kind of verify what that change was, but that's okay. All right? So the forwarding address is the same. It does not have anything to do with the router ID. It doesn't change how we decide to reach that particular destination. All right? So let's look at router 4's routing table. Let's see how we get to that forwarding address. One of the things that we can do to identify which ABR we're going to choose is we can always do a show IP OSPF database border routers. If I spell it correctly, database border routers. Show IP OSPF database. Oh, not database, sorry. Just border routers. All right? Now we can see there are 3 listed here. One is an ASBR, that's router 2, and then 2 are listed as ABRs. So we don't even identify in area 0 that router 3 is an ABR. That's already a significant difference. But the reason why we can see router 2 as an ASBR is not because of the type 5 LSAs that are coming in. It's because of the type 4 LSAs that are being generated at the ABR of that area to describe reachability to that ASBR. There are no type 4 LSAs being generated by the ASBR in area 2, which is router 3. The forward metric will identify whether or not we can use equal cost multipath load balancing, ECMP, on those external routes. As long as that forwarding metric is equal, then we can use equal cost routing. When we look at the database, we route once, but we can still have multiple entry points into the area. As long as you are advertising the route, if you're an ABR and you have reachability to that forwarding address, you can be used in the path to reach that destination. Let's see if that's actually happening in this case. So show IP show IP SAF 33.33.33.33 detail. All right, so we're not doing any kind of equal cost routing in this particular case, which makes sense, right? We have an equal cost to reach the ABRs. It costs 10 to reach ABR1, router 1. It costs 10 to reach ABR2. But because the path is not the same, it's not going to be able to use both paths. Let's actually trick it to thinking that the path is the same. So what we're going to do is we're going to make the cost of this serial link 10, which then should equal the cost of this serial link. So router 3 and router 5, we're going to go into serial 20 and change the cost of that link. Let me just do a quick show IP interface brief. Serial 20, all right? Interface serial 20, IP OSPF cost 10. And I'll do the same thing on router number 5. Show IP interface brief. Config T interface. Config T. Interface serial 20, IP OSPF cost 10. Now what should happen on router 4 is that router 4 should eventually, hopefully, identify that we can do equal cost load sharing. There we go. All right. So now in this particular case, 33, 33, 33, 33 is going to be reachable by both ABRs. 14.1 is router 1 and 14.3 is router 3. Let's see how that changed who's advertising the external route. Show IP OSPF database external. And we can see that, actually let's do the database by itself first. And we can see that for the type 5 LSA, router 5 is still only originating the reachability information for the 33 subnet. Again, it doesn't matter. If we're running ECMP or not, it makes no difference because only one of the ABRs needs to advertise the route. That does not define reachability to the external destination. If I wanted to see the hash buckets for the forwarding process, I do a show IP Ceph 33, 33, 33, 33 internal. This will show me the hash buckets that I'm using for the equal cost load balancing. So 2 different hash buckets were created, and we have 2 different adjacencies here, 14.1 and 14.3, identifying the path list based on the route. The next hop is 14.1 and 14.3, and we've identified essentially 2 ways of reaching that destination. We're doing a per session for receive IPv4 address for that hashing. So if I do a trace route to 33, 33, 33, 33, we can see that we have 2 different ways of reaching that destination. 14.1, 14.3, 14.1, 131.2, 13.2, 131.2. All right? Remember, Ceph is actually what controls how the traffic is load balanced to a destination. The routing table does not control load balancing. It just feeds that forwarding information base, and the forwarding information base is the software Ceph table that then gets written down to the ASIC or the line card if you're doing some sort of hardware forwarding. Only one router was advertising reachability because we already saw this, the details of the LSA shows that the forwarding address is a non-quad 0 value. Show IP OSPF database external for 33, 33, 33, 33, non-quad 0 value. All right? Why is this significant? Because it allows us to figure out how we're going to route to that particular destination based on Cisco Express forwarding. All right? We can figure out how we're going to route. Everything is done automatically. We don't really have to control it, right? We're going to talk a little bit about that automatic process in a minute here, because I haven't really gotten into the details of how the election takes place. I'm going to draw a diagram and kind of go through the process a little bit. All right? Now, in this particular case, ECMP was forced because we changed path metrics to make the paths look equal. But what if we don't want to do ECMP? What if we only want to use one device for the forwarding? Who does the translation? Who accepts the traffic, etc.? Maybe this is not something you would see in the real world. Obviously, we would prefer to go through router 1 given the path metric. But they may ask you on the CCIE to do these modifications outside of the norm because they want to test your ability to understand the concepts. All right? Who does the translation? Who accepts the traffic? The translation is going to be based on the router ID. So let's talk about that a little bit here. Let's talk about that concept, all right? Because we haven't gotten into a whole lot of detail. I wasn't originally going to do this, but I thought it was pretty important to understand. So what I want to do is I want to first kind of give you guys a diagram of what we're talking about here so that you can have an idea as I go through this process of what we're discussing. So let's say that we've got a router here, and we've got a router here, and a router here. I'm not going to put in all the IP addresses. I'll add them as we need to go. But let's say that this is a link to router, well, this is R1, this is R2, this is R3, and this is R4. All right? We've got a link here, and a link here. We're basically kind of, I should have just written them the same router numbers, but we're basically kind of duplicating, not exactly, but kind of the process that we were talking about in our own topology as well. We've got this external network here. We'll just call it the 33 subnet. Whatever, I don't want to put everything in there. That's in EIGRP. Let me draw, in fact, some of the boxes here. So let's say that this area here, that's my NSSA, area 1. Well, we'll make it area 2 in this case because that's what we have in our diagram. We're running EIGRP in this network, so that's our external domain. And we're running our OSPF area 0 here. All right, so we'll just call that area 0. So again, we've got two routers that are acting as ABRs. Router 4 is our ASBR. And as far as router IDs go, let's just assume that the router IDs are the router numbers. So for this router, the router ID is 1.1.1.1 and 2.2.2.2, etc. All right? So this is 3.3.3.3 and finally 4.4.4.4. So we know how router 4 is going to advertise this route. It's going to advertise it as a type 7 route with the p-bit set. Router 2 and router 3 are then going to originate those routes. Let's assume that all the paths are equal cost. They all have the same metric. So what happens in this case? What I want to look at, and this is really kind of why I'm going off on this tangent, is who does the NSSA type 7 to type 5 translation? How can we use the forwarding address to control routing towards the external routes that have been brought into the OSPF domain via the NSSA? And that's really the topology that we're going to be using. Router 4 is redistributing a prefix, the 33 prefix, into OSPF. And we already know that all the routers are going to have reachability. Only one ABR, just like we saw in our topology, that's connected to the NSSA is elected to do those type 7 to type 5 translations, even though they're both receiving the route with the p-bit set so that they're both allowed to do the translation. How is that decision made? That's something we haven't talked about yet, but it's actually a pretty simple concept. The decision is based on who has the highest router ID. That's it. So if we look at the OSPF database, if we were to kind of dive into this OSPF database for that external prefix, we should see that router 3 is doing the advertisement of the type 5, the translation of the type 7 to type 5, because it has a higher router ID than router 2. It has a router ID of 3.3.3.3 as opposed to 2.2.2.2. So if I wanted to confirm that, I would just simply do a show IP OSPF database external 33 on that router, and it would confirm that the 3.3.3.3 has done the type 7 to type 5 translation. So if we were to make router 2's router ID higher than router 3, router 2 would be the router that does the translation. And that happens automatically. All right, we could do that in our topology. I am going to do that a little bit later on. Because I want to show you guys how we can manipulate this process manually as well. But we know that if we change the router ID, it's a preemptive concept, unlike a lot of the things that happen in OSPF that's non-preemptive. In this case, this is a preemptive concept. All right? So once we change that router ID, that's going to change who does the translation. Now, the forwarding address is an IP address that should be used to resolve or solve the shortest path tree to that particular external prefix instead of solving the path to the node who advertised the prefix. We saw that with type 5 LSAs. We're resolving the shortest path to the node that's advertising the prefix with our type 4s and our type 5 LSAs, as opposed to the shortest path to the external prefix. So since we don't have this technically built, let's just talk about it. So we can't really see, we can see it in our topology. We've kind of already analyzed that. It's really just a matter of checking the best path to reach the ABRs, right? And the shortest path to reach those particular ABRs. The only thing that I really want to clarify is why the forwarding address was actually set to that value, whatever value it might be. In this case, we don't have the IP addresses on router 4, so we don't technically know what that forwarding address would be set to. The forwarding address is actually always decided by the ASBR that's originating that route. In this case, it would be router 4. In our case, in our actual live topology, it would be router 3. The forwarding address is elected a lot differently than what you would expect. And that's one of the things that I wanted to talk about is how this forwarding address is selected, because it's something that we had a little bit of confusion about on one of the last lessons, and I wanted to make sure that we understand it. The whole point of having this forwarding address that was introduced in OSPF to avoid extra hops when traffic's routed to some sort of external domain, especially if it comes in from multiple locations. So let's say we have two routers in OSPF domain that connect to the external domain, but we're only advertising that route. Now we know, as an example, the forwarding address in a normal area would always be a quad 0, and we'll use different resolution. The forwarding address, if it gets set to quad 0, we just simply redistribute the route, and the next hop doesn't really matter. The forwarding address doesn't matter in this particular case. All right? There are some conditions that have to be set in order for the forwarding address field to be a non-zero address. First of all, OSPF is enabled on the ASBR's next hop interface. That's number one. The ASBR's next hop interface is not passive, so it has to be participating in OSPF. All right. The next hop's interface is not point-to-point, and the next hop interface is not point-to-multipoint. So these are things that we didn't talk about previously. And in our particular case, the next hop address is loopback. All right. So that's why we chose the loopback address. All right. Finally, the next hop address interface has to fall under a network range that's specified as part of OSPF. So we meet all those conditions. In our particular case, in this topology here, let me pull that up. In this topology here, this 192.68.3.1 address is enabled. It's not a passive interface. It's not point-to-point. It's not point-to-multipoint. I wonder what would happen if we did change it to one of those values. Let's go ahead and try that real quick. Because we don't have, if I do a show IP OSPF interface brief, it doesn't look like we have on router 3. Well, we have a couple of loopbacks, but we know that serial is point-to-point. Ethernet 1.0 is broadcast. So I'm curious if the next hop would end up being set to 13.2 if we changed our loopback to point-to-point. Let's go into interface loopback 0, IP OSPF network point-to-point. Now let's go over to router 1, show IP OSPF database. See if we still have our external route. We do. And if I do a show IP OSPF database NSSA 33, 33, 33, 33, the next hop is still 3.1. I was researching this because of our discussion that we had the last time. And I wanted to try and clarify some of the concepts about how this next hop address was advertised. Let me do a clear on this one too, because we might have some aging stuff going on. Clear IP OSPF database. Let's do that. Clear IP OSPF database process. Silly. All right. Looking at the database, thinking about the process. All right. Show IP OSPF database. We shouldn't have anything right now because it's should be taking us a while to reconverge. Let me check my neighbors. Show IP OSPF neighbor. Yeah, we're converging pretty quickly. All right, so now let's do a show IP OSPF database NSSA external 33. Well, that's really interesting to me because I pulled this information in my notes. I kept notes, copious notes on this as a matter of fact, from the Cisco documentation. And that document, if I recall, was published in, well, it was in 2005. So this may be old information. Because previously what they had stated was the value of the forwarding address, whatever value that we choose, it can be a 0 or a non-zero value. But in order for it to be a non-zero address, the next hop interface, and I wonder if they're referring to, in this case, the Ethernet network. Now that I'm thinking about that, next hop may not necessarily mean the loopback. It would mean reachability, how we reach that particular destination. So it looks like I'm going to have to table that process or that discussion again. That's okay. And I don't know that that's actually the most important concept to understand out of this. You know, how that non-specified or that specific scenario is selected. But the reason why I wanted to discuss it is really because usually you would want to be receiving an external prefix from a different router as opposed to the one that's actually doing the redistribution, where the external prefix actually exists on the ASBR itself. And that's what we're doing in this particular topology. All right. If we get a non-zero forwarding address, when the OSPF network is point-to-point for that interface, I suppose that could happen. It looks like it's happening in this particular case. But this may be something that we have to investigate a little bit later on. I have to decide whether or not it's something that we really want to get into details on as we move forward. All right. There is something in RFC 3101. I pulled that out as well when I was updating my notes. And I actually have a quote here. It says, when a router is forced to pick a forwarding address for Type 7 LSAs, preference should be given first to the router's internal address, provided internal addressing is supported. If internal addresses are not available, preference should be given to the router's active OSPF stub network address, which in this case would be our loopback. These choices, that wasn't in the quote by the way, these choices avoid the possible extra hop that may happen when a transit network address is used. Meaning, if we had, since we're originating this route internally on the ASBR, router 3, this is a connected route on the router. There is no transit path to reach that external prefix. Does that make sense? So I could potentially have an external link on this router. I could have an external link on this router that goes to some other domain, and those external prefixes are being advertised, and this would end up becoming the forwarding address for those particular prefixes, meaning that we would have essentially an extra hop, the extra hop being router 3. In our case, it appears as though that's happening as well because the loopback is being advertised as the forwarding address, whereas you would expect that the forwarding address would be the closest interface to that destination. And that's the part that's kind of tripping me up a little bit because different documentation has different ways of describing this. But let me go ahead and finish up the quote here. I'll repeat. These choices avoid the possible extra hop that may happen when the transit network's address is actually used. When the interface whose IP address is the LSA's forwarding address transitions to a downstate, the router must select a new forwarding address for the LSA and then re-originate it If one is not available, the LSA is going to be flushed. All right? So in our case, we can't do that, right? We can't originate, the forwarding address has to be, in our particular case, the loopback, because that's the only other interface we have. All right? When we talk about internal addresses, we're talking about loopback addresses. That's what they mean by internal versus external. All right? So the order, as far as I could tell, and I could be wrong on this, but I would have to go back and verify this, it would be the newest OSPF-enabled loopback interface, IP address. In some iOS platforms, it appears to be the oldest. That was one of the reasons why when we added a loopback, it didn't change the forwarding address. The newest OSPF non-loopback interface that was connected to a transit stub network, which we don't have in our particular case, or the newest enabled non-loopback interface IP address that's connected to a non-transit stub network. All right? Probably making it a little bit more confusing than we need to, but it appears, though, with our iOS that the forwarding address is based on the oldest loopback interface as opposed to the newest loopback interface. I know how we can actually test this theory. And I'll do this one final test, and then we will move on to finish up the rest of our discussion here. So if I do a show IP interface brief, I can see that I've got loopback 100. Now I'm going to create loopback 101, and I'm going to do an IP address of 34, 34, 34, 34. And I'm going to go into router. Let me do my show IP protocols. Okay, router EIGRP 100. And actually, let's do a show run section EIGRP. Let's see if that's already part of the process. It is not. So let's go ahead and do network 34.0.0.0. So now in router 4, I should see both of those. Show IP, OSPF database, and I should see 34, 34, 34. If I do a show IP, OSPF database, NSSA external, 34, 34, 34, 34. Well, that's interesting. We can see the link ID being advertised, but we don't have reachability. Show IP interface brief, show IP OSPF database, NSSA, or self-originate. So we're definitely originating that. Show IP OSPF database, NSSA external 34, 34, 34, 34. All right. So it does have a forwarding address of 3.1. It could be a convergence thing. Let's go back to router 4. Show IP OSPF database external 34, 34, 34, 34. Routing bit is set. That's actually strange. Was I doing NSSA or was I doing external? I was doing NSSA. Never mind. Obviously, it's not coming in as a type 7 here. I should have just done external. So we do have reachability. All right. Now here's the experiment that I wanted to make. Because I did create a new loopback on router 3, show IP interface brief. Loopback 101 is the newer loopback. Loopback 100 is the older loopback. So if I come into interface loopback 100 and I shut that down, of course I'm going to lose my 33 subnet. I still have reachability to 34. But what I'm wondering is whether or not the, dang it. I did it the wrong way. Remember, it's got to be the OSPF loopback, not the EIGRP loopback. Remember, on router 3 we have loopback 0 as well. Do show IP interface brief. Loopback 0 is participating in OSPF. So let's go and create loopback 1. Interface loopback 1. IP address 192.168.34.1, 255.255.255.0. Well, that doesn't matter. We can make it 255. And let's do IP OSPF 1 area 2. Now this is considered the newer loopback, right? Show IP interface brief. Let me go ahead and turn on loopback 100 again because we don't need to shut that down. So now 34.1 is considered to be the newer loopback. Based on the documentation that I read, it would indicate that that newer loopback should become essentially the forwarding address for the prefixes on router 4. But it didn't. And that's the same thing we ran into the last time we did this exercise. I was under the impression that it was based on the highest IP address, which I was wrong. And based on the documentation, it should be based on either newest or oldest loopback. Now clearly if I come into router 3 and I shut down interface loopback 0, we should see router 4, from router 4's perspective, that forwarding address would change. It might take a while for the convergence. Let's do a clear IP OSPF process. And we'll do the same thing on router 3 to kind of trigger this. Do a clear IP OSPF process. All right, do show IP OSPF database self-originate. So we're sending in the prefixes NSSA 33, 33, 33, 33. All right, so the forwarding address is 34.1. Now that makes sense, right? Because 3.1 no longer exists. Now the question is, will it change if I go ahead and bring up that other loopback? I'm guessing not, because now that would be considered a newer loopback. Interface loopback 0 no shut. That would be considered a newer loopback. And also, the other thing I wasn't able to discover was whether this was a preemptive or non-preemptive process. And that kind of throws a wrench into the system, right? Because if it's a non-preemptive process, the election really doesn't matter. As long as the interface that's being advertised at the forwarding address is active, it shouldn't matter what the election is, because once I'm elected, I stay that way. Show IP OSPF database, NSSA external 33, 33, 33, 33. So that's interesting. It did change. We did not bring down the 34 interface. The forwarding address did change to 3.1. So I'm going to do one more experiment. I promised that was the last one, but I think I want to just check one more thing. I'm going to create another loopback. I'm going to give it an even lower address to see if that interface, so let's do interface loopback 2, IP address 1.1.1.1, 255.255.255.255, IP OSPF 1, area 2. This is kind of how you tend to play with things, and on the CCIE, it's most likely not going to be something you're going to have to worry about. But you know, when I have a curiosity about something, I like to kind of play around with it and see what the behavior is, especially when the documentation is a little bit confusing and we don't necessarily understand. You know, one document says one thing, another document says another thing. Show IP OSPF database NSSA 33, 33, 33, 33. So it did not change, and that experiment, show IP OSPF interface brief, was for the purpose of identifying whether or not a lower address was used. Clearly, the state of the interface doesn't matter because it was 34.1, and then this point-to-point became the forwarding address. So what does that leave us with? I'm not going to do any more experiments. I promised I was only going to do that last one. But it leaves us with a couple of questions, right? Is it based on the loopback interface number? Did loopback 0 take over because it happened to have a lower number, lower interface number that's not typical or atypical for OSPF? Did it take over because it had a lower IP address? Did it take over because it was originally part of the OSPF process? We can certainly go into interface loopback 0 and change the address, 192.168.35.1. We know it's a preemptive process because it did change without clearing the process, so we at least answered that question. Show IP OSPF database NSSA 33.33.33.33. So that's interesting. It changed to 34.1 even though loopback 0 never went down. All we did was change the address. So it's starting to look more and more like there's a couple of things, because certainly 1.1.1.1 is lower. Let me make sure I'm running OSPF on that interface. Show IP OSPF interface brief. Yeah, so loopback 2 is running OSPF. So it's strange, right? Because you thought, well, it's the lowest IP address, then loopback 2 would have taken over. I changed loopback 0 to 35, and loopback 1 took over. So it seems like we're just kind of creating more questions than answers. If I go back to interface loopback 0, IP address 192.168.3.1, do show IP OSPF database NSSA 33.33.33.33. I'm going to expect that in this case we would switch back to, so it did not switch back to 3.1. Interesting. All right. Well, question unanswered, if you will. It looks like there's some kind of strange behavior happening, although I wouldn't consider it strange, like in a sense it's not supposed to be doing what it's doing. It's just not really answering our question as to how that forwarding address is being selected. In the end, it doesn't really matter. I think that the only thing that you would ever be required to know on the exam is how to manipulate that forwarding address at the ABR. All right? We know that going back to our lecture, we might want to use one device for forwarding as opposed to the other device. So let's just go back to router 4. We made a lot of changes. Let's do a show IP Ceph for 33 detail. And we can see that we are still doing per destination load balancing because we manipulated the cost of the serial link to look like the cost of the Ethernet link. As far as who's doing the translation, so IP OSPF database external 33.33.33.33. It looks like router 5 is doing the translation. For that prefix, it should be the same for both of them. And router 5 is doing the translation for that prefix. All right? Now, if I was to reset the node, and that's going to cause us to redescribe the graph, and once we do our convergence, we can see that, well, actually, let's change it so that we just talked about the fact that the router ID of the routers is what's going to determine who is actually advertising that prefix. So the router ID of router 1 versus the router ID of router 5. So let's go to router 1, show IP protocols router, pipe include router, so, or ID, I should say. The router ID of router 1 is 1.1.1.1, and I would expect for router 5 it's going to be 5.5.5.5. Show IP protocols, pipe include ID, and it's 5.5.5.5 there. So let's go ahead and change it on router 1. Just to prove that concept that I described earlier about who's going to be actually doing the type 7 to type 5 translation. Router OSPF 1, router ID 11.11.11.11. Do clear IP OSPF process, yes. And we should see, once our neighbors all come back up, if I go to router 4, and I should see now that router 1 should end up advertising those prefixes eventually. I could probably do a clear on here as well, so we don't have to wait for the age to expire. Show IP OSPF, let's do this one. All right, we'll wait till we converge, and we should see that router 1 is now originating that external route as opposed to router 5, eventually. All right, let's see, come on, you can do it. Show IP OSPF neighbor, still doing the election. We see the routers, there we go. All right, and sure enough, router 1 is originating that route. But if I do a show IP route, show IP Ceph, excuse me, 33, 33, 33, 33 detail, we're still doing ECMP. All right. Also, incidentally, the routing bit will always show us that that's the router that we're going to go through to reach a particular destination. And on different routers, we'll see whether or not the routing bit is set. We might even see the same prefix on both routers. But based on our metrics right now, we still have ECMP to the forwarding. Based on the forwarding metrics, we're still using ECMP to reach those destinations. We're going to choose the SPT to the ABR that's going to be the shortest path. But in our case, because they're equal, we're choosing the path through a particular router. Now, we can influence how that path is selected by modifying the cost if we want to. And we actually did that to force ECMP to take place. We changed the cost of the serial link to 10 so that the path looked the same. Now in the CCIE, we talked about this in one of our previous lessons, they may have you do something, which you may know how to do in a certain way, but they may want you to change, influence that process in a way that is not really conducive to kind of like an ordinary way of doing it, if you will. That was a very horrible way of saying that. But what I mean to say is that they want you to change something, but don't change it this way, which would be the normal way that you would change it. So path selection, of course, we change the metrics. We're going to choose a different path. All right? So in our case, the other option that we have is to change what the forwarding address is. All right, if we did a show IP OSPF database NSSA on each of the ABRs, we would see that the forwarding address, we'll just do it on one, we don't have to do it on both. But if I do a show IP OSPF database NSSA for 33, 33, 33, 33, the forwarding address is listed as 34.1. And that's going to be the same on router 1 and router 5. All right, so we're seeing who the translator is. On router 4, we would see who the translator is, but not necessarily the route. If we want to change this behavior, what we would do is we would go into the router and we would specify whether or not we want a particular router to win for the translation. So if I go to router 4, we know based on what we just looked at, well, I can see it right here actually, that router 1 is the one that's advertising the route. So here's the first part of the decision. I want router 5 to advertise the route. I don't want the router ID to be the determining factor for who advertises this external prefix. So I'm going to go into router 5, go under OSPF 1, and I'm going to say area 2 NSSA translate type 7 always. So this, there's now a bit or a flag that's being set in this router, in the hello packets, and how this router communicates to the other routers within the area that says, you know what? I'm going to be the one that's always translating type 7s to type 5s. So if I go to router 4, and I do a show IP OSPF database external for 33, 33, 33, 33, I can see that router 5 is now the translator for that external prefix. If I do a show IP Ceph for 33, 33, 33, 33 detail, I can see I'm still doing per destination load balancing. So that hasn't changed. My routing to the prefix hasn't changed. It's just a matter of who's doing the translation. And if I did a trace route, we would see the same thing. The trace route, the path didn't change from the perspective of the routers. All right? That's one option that we have. And they may ask you to do that in the CCIE. They may say, you know what? Make sure that router X is the one that's translating the routes. And you might decide, well, I know how to do that. I'm just going to give it a higher router ID. But they might specifically say, you know what? You're not allowed to change the router ID, so you have to do it a different way. All right? Now, what if I wanted to change the behavior of the forwarding address? We can see that the forwarding address is still listed as 192.168.34.1. And this is a little bit more dangerous, but we can do this, and this is basically for traffic engineering. I'm going to go into router 5. All right? Now, if you recall, before we do that, let's go back to router 4. Show IP, OSPF, database, external, 33, 33, 33, 33. So we know router 5 is the one that's advertising the prefix, but if I do a trace route to 33, 33, 33, 33, we can see that we're load balancing between router 1 and router 5, right? 14.1, 14.3, 14.1, etc. Okay? So now I'm going to go into router 5 because router 5 is the one that's originating this route now. I'm going to go back into OSPF 1. And I'm going to say area 2 translate, area 2 NSSA, sorry, translate, type 7 always, and now I'm going to add a suppress FA. Suppress FA means suppress the forwarding address. So if I go to router 4 now and I take a look at that external route, the forwarding address is now listed as quad 0. What does that mean from the perspective of routing? That means that now we no longer can use our ECMP. If I do a show IP CEF 33, 33, 33, 33 detail, we're no longer doing equal cost load balancing because we're using more of a traditional way of resolving the path to the translator rather than doing it to both destinations. So if I do a trace route to 33, 33, 33, 33, we can see now we're only taking one path. It would be nice if you could do this per prefix, like per external prefix. Unfortunately, we don't have that capability. We'd have to do some other kind of crazy traffic engineering to control this. But on the CCIE, they may say, make sure that all the external routes take this particular path. Now, here's the question. Does that happen even if the metric is worse, right? So we changed in our topology this serial link metric, path metric, to 10. And now we're forcing the traffic essentially to take this path. So let's go ahead and make this path, or switch it back to its original cost. So I'm going to go to router 3, config T, interface serial 20, no IP OSPF cost. And I'll do the same thing on router 5. Interface serial 20, no IP OSPF cost. And if I do a show IP OSPF interface, show IP OSPF interface brief, we can see the cost of the link is now 64. Go back to router 4 and see if we're still forced to take that path. And we are, right? So if I do a show IP OSPF database, external, 33, 33, 33, 33. We can see that we're still going to router 5. Because the forwarding address is quad 0, that means we're going to use our SPT and resolve the SPT to the ABR as opposed to the external node or the external network. All right. Why would we do this? Well, we may want to route all of my kind of inter-area LSAs through one ABR, but I want to route all my external LSAs through a different ABR. All my external routes that I'm learning from an external prefix. All right? So let's go back and take that out. Do show run pipe section router. router OSPF 1, and let's take that out. Let's go ahead and make the path the same as well. IP OSPF cost 10, and same thing on router 3. IP OSPF cost 10. And we should see back again from router 4's perspective, the trace route should, we should be getting our forwarding address again, and we should be doing equal cost load balancing again. All right. What if we aren't learning the forwarding address in OSPF? All right. And I was kind of keeping my notes on this, and I thought, well, you know, maybe how can we do that, right? How can we make it so that the forwarding address is not part of OSPF? I'll see if I can try to do this. My notes aren't very clear here, but if we did an eBGP pairing relationship between router 4 and router 3, and took out the 34 address from OSPF, and well, we don't want to take it out, because if we take it out, then another interface would become part of the forwarding, would become the forwarding address. So we still want to leave it in, but if we do eBGP, we should learn about that prefix through eBGP, which has a lower administrative distance than OSPF. So what I'm going to do is I'm going to create, and this is kind of one of the last few things that we'll be doing here, and then we'll wrap it up, is I'm going to create an eBGP pairing relationship between these two routers, and then I'm going to advertise that loopback that's being used as a forwarding address into BGP, so that router 4 learns about that address through BGP and not through OSPF. All right, let's give it a shot here. All right, so config T, router BGP 4, neighbor, what do I want to use as the neighbor address? Well, we can use the reachable prefix. Let me go to router 3, do show IP interface brief. We'll just use the Ethernet interface as the remote AS. We'll just call it, since it's router 3, that. We'll also have to do eBGP multi-hop. Should be eBGP multi-hop. There we go. And we'll have to add the network that we want to advertise. I don't think I need to add it on this side. I'll just add it on the other side because we want to include that loopback as part of the BGP routing process. So let's go to router 3, router BGP 3, neighbor, and let's go to router 4, do show IP interface brief, and we'll use the Ethernet, this guy right here. These are already, we have IGP reachability with these addresses through OSPF, so that's obviously going to be one of the requirements for establishing this relationship. Remote AS, we'll call it 4, and neighbor eBGP multi-hop. All right, I may have to specify the number of hops, but nope, we're good to go. Usually if you don't specify it, it just goes to the max. So we've got a BGP relationship. Now what I want to do is I want to take that prefix, do show IP interface brief, do show run interface loopback 1. I want to take this prefix and I want to put it into BGP. So let's do a network of 192.168.34.1 with a mask of 255.255.255.255. Now what should happen is on router 4, show IP route, I should be getting a BGP route for that prefix, 34.1. And because it has a lower administrative distance than OSPF, has 20 instead of 110, we're going to be using that route, that BGP route to reach that destination. So if I do a show IP OSPF database, external 33.33.33.33, we still see the route. We still see the route in the database, but guess what's missing from the route? The one thing that we always look for in any kind of route in our database is whether or not the routing bit is set. And we can see that the routing bit is no longer set. If I do a ping to 33, 33, 33, 33, we no longer have reachability. This is something that they could potentially put in the troubleshooting section where they're trying to screw with your mind and say, you know, you're looking at the database and you're saying, well, the route's there. I can see the 33, 33, 33, 33 network, but I can't reach it. But I can ping the 192.168.34.1 address. Right? So you're thinking, wait a minute, I can get to the forwarding address, but I can't get to the external network. And they may actually say, well, you need to fix this, but you can't change any of the routing. And that's where you would say, okay, if I can't change any of the routing, then what do I have to do? I have to change the forwarding address. So I might force the ABR to suppress the forwarding address so that I would have reachability. See what I'm saying? There's all kinds of strange things that they could get you to do. All right? The administrative distance of the BGP route was 20, not 110. As we see, the routing bit is not set on this particular route. Remember, we're routing to, whoever's doing the translation is completely arbitrary when we're doing a 7-to-5 translation. We're getting the database, the route in our external database. Router 1 is doing the 7-to-5 translation, but because the forwarding address is not reachable, then we cannot resolve the tree, right? And OSPF can't really guarantee this route. So now if we take out the BGP process, obviously that's going to fix the problem. All right, let's do one more experiment. We've already seen how router 4 works. If I do a ping to 33, 33, 33, 33 with a repeat count of maybe 10,000 or 100,000, now if I go into router 1, remember, we have to do this on router 1 because router 1 is the one that's doing the translation. Router OSPF 1, and I type area to NSSA, translate, type 7, always, suppress, FA, go back to router 4, now we have reachability. Right? So it happened pretty quickly, and that may be what they make you do on the exam. They may say, you know what? You're not allowed to change any routing. You can't change the BGP routing. You can't change how the tree is being resolved. And you have to come up with another way of fixing the problem. That make sense? This is also extremely useful. There's a use case scenario for this. When you're routing across a service provider network, the transit links that exist in the service provider network don't necessarily need to be advertised into OSPF or whatever protocol, in this case OSPF, because the transit links are only there to pass traffic for end-to-end reachability. They're not used, they're not being advertised to the clients so that the clients can reach those transit networks themselves. So we may want to suppress or hide the fact that those transit links exist, and that's where this would come into play. All right. There is a way we could actually do that to suppress advertisements of links. Let's say, let's go to router 4. If I do a show IP route OSPF, well, let's consider in our topology here that the transit link is this. Well, we're going over router 1 in this case. So let's say this 13 subnet is a transit link. And we can see in the routing table of router 4, the 13 subnet exists. It's coming in as a type 3 LSA, and it's being advertised by router 1 and, well, potentially router 3 as well. So I could come into router 1, interface, let's see, let's do a show IP interface brief. Try that again. Ethernet 1, 2. Yeah, Ethernet 1, 2. Interface Ethernet 1, 2, and I could issue the command IP OSPF prefix suppression. All right, I want to do this on both sides of the link. Router 3, show IP interface brief. So that's going to be Ethernet 1.0. And what should happen in this case is router 4 should no longer see that prefix in its routing table. It should happen. It might take a little bit. We might have to, yeah, it's gone, right? So here it is up here, 13.0, and now it's been suppressed. So a lot of times service providers will do this, and that could affect overall routing, right? That route is no longer listed in the database. Do I still have reachability? Absolutely. Because it's just a transit link. We don't really need to know about that particular prefix in our database because it's just being used to pass traffic. We're not trying to reach a destination within that network. All right, guys, that's it for today. Thankfully, the computer worked out a little bit better today, but took a little bit longer than I thought it would, but I wanted to make sure we were thorough. What we're going to do next time, we're just about wrapped up with OSPF. We've only got a few other lessons to go through. Pass selection is going to be our next section. And then most likely I'm going to go ahead and combine the last 4 lessons into 2 different lessons. So we'll have OSPF authentication with enhancements. We'll do that together. And then OSPF summarization with configuring summarization. We'll do that together. So we really only have 3 lessons left for OSPF. And then we're going to move into our DMVPN discussion, which is a much shorter section than EIGRP and OSPF was. All right, guys, so if you don't have any questions, we'll see you in the next lesson.